Imagine waking up to see California's iconic coastline suddenly perched 6 feet higher than it was yesterday. Hundreds of miles of land, from San Francisco to Los Angeles, just lifted overnight with no earthquake, no warning, and no explanation. Beaches are stranded above the waves, ports crippled, sea life marooned, and every sensor from NASA's JPL to municipal GPS networks confirms the impossible. What should take thousands of years happened in hours. Geologists are stunned, arguing over whether this is catastrophic land movement or a data mirage. But one terrifying fact remains. Experts cannot explain the cause, and the land is still rising. Is this the start of an unprecedented geological disaster, or proof that everything we think we know about Earth's mechanics is wrong? The answer begins with what science says should be impossible. California's coastline sits on the meeting point of two restless tectonic plates, the Pacific and the North American. Over millions of years, this boundary has produced a landscape in constant, measured motion. Most of the time, that movement is almost invisible. The land creeps at a pace of 0 to 4 millimeters per year, a rate so slow it would take a lifetime to notice even a few inches of change. This is the natural order along the coast, confirmed by decades of records from ground-based GPS, satellite radar, and tide gauges. Scientists at places like NASA's Jet Propulsion Laboratory track these shifts with extraordinary precision. Their instruments can detect the ground rising or falling by less than the thickness of a fingernail. In the Santa Barbara Basin, for example, carefully calibrated sensors have measured uplift of just 2 or 3 millimeters a year, barely enough to register on a ruler. In other places, like Long Beach, human activities such as oil extraction or groundwater pumping sometimes nudge the land up or down by a few centimeters, but always at a gradual pace. The majority of California's coast actually sinks rather than rises, as groundwater is drained or sediment compacts beneath sprawling cities. Even when the land does lift, the process is slow and steady. Every change is logged, compared, and checked across multiple networks: satellite interferometry, ground stations, and tide markers. Each layer of data reinforcing the same story. Vertical land motion here is measured in millimeters per year, not feet per day. Marin Govorchan, a remote sensing scientist at JPL, puts it plainly. In many parts of the world, like the reclaimed ground beneath San Francisco, the land is moving down faster than the sea itself is going up. For geologists, these tiny numbers are the baseline, the expected rhythm of a living, shifting coast. Anything faster, any sudden leap, would be more than unusual. It would be unthinkable. No one in the scientific community had ever seen numbers like this. The idea that California's coast could jump several feet overnight wasn't just unlikely. It was, by every measure, impossible. In places like Santa Barbara, the most dramatic uplift ever recorded topped out at 3 millimeters a year. That's about the thickness of a credit card, and it took 12 months to get there. Even the rare cases of human-caused uplift, like groundwater recharge in the Santa Barbara Basin or fluid injection in Long Beach, barely pushed the land up by a centimeter or two over an entire year. The rest of the coastline, including major cities, usually sinks instead of rising. So when GPS stations up and down the coast started reporting vertical jumps of 6 feet in a single night, alarm bells didn't just ring. They shattered. These instruments are built to catch the subtlest shifts, logging every movement with precision down to the millimeter. Their data is checked against satellite radar, tide gauges, and old-fashioned leveling surveys, all cross-validated by teams of analysts at places like NASA's Jet Propulsion Laboratory and the United States Geological Survey. The odds of every system failing at once are astronomical. Marin Govorchan, a remote sensing scientist at JPL, summed up the disbelief. If these numbers are real, we're not just rewriting textbooks, we're questioning the ground we stand on. The accepted science says that only a massive earthquake or volcanic eruption could move the Earth this much, this fast. But the seismic networks were silent. No tremors, no rumbles, not even a blip. The land just rose, quietly, everywhere, all at once. This left experts with a chilling choice. Either the world's most advanced monitoring network had failed on a scale never seen before, or something was happening to the planet that no one could explain. As the data poured in, teams scrambled to audit every sensor, every satellite pass, every line of code, desperate to find a glitch or a sign of new physics at work. Engineers at the Jet Propulsion Laboratory began their audit with a single question: could the data be trusted? The first step was to retrieve the original Rhinex files from every GPS station reporting the jump. These raw files, unfiltered and time-stamped, serve as the backbone of any vertical motion analysis. Each file was checked against station logs, antenna types, maintenance history, and even the soil conditions beneath each concrete monument. The team combed through frame references, looking for evidence of a silent shift in the global coordinate system that might mimic a sudden rise. A simple misalignment in the International Terrestrial Reference Frame could, in theory, create the illusion of the ground leaping upward. But the anomalies didn't stop there. Atmospheric modeling became the next line of defense. Engineers pored over tropospheric and ionospheric correction tables, searching for spikes caused by storms or solar activity. Even a brief lapse in atmospheric calibration can introduce centimeters of error, especially during periods of rapid weather change. Yet, the supposed uplift dwarfed any known atmospheric artifact by orders of magnitude. Cross-checks extended to INSAR radar stacks and tide gauge logs. If the GPS signals were corrupted, the radar satellites and coastal gauges should show no corresponding movement. But the first batch of INSAR data, processed independently, showed the same impossible step in elevation. Engineers scribbled notes in their field books: frame error, multipath, unwrapping glitch. Each possible culprit was tested and ruled out. As the audit deepened, the team's confidence in the raw data wavered. The usual suspects, reference frame slips, multipath reflections, and atmospheric noise, could not explain a 6-foot vertical leap. With every layer of validation, the mystery only grew. The process, meant to calm nerves and restore order, instead left scientists staring at numbers that refused to make sense. Every anomaly in geophysical data has a history of false alarms. The audit team at JPL knew the difference between a real crisis and a digital ghost depended on catching the smallest errors, the ones that slip through when everyone is desperate for answers. Multipath distortion was the first suspect. When GPS signals bounce off buildings, water, or even parked cars, they can trick a receiver into reporting. The ground is higher or lower than it really is. But the coastal GPS stations, perched on open bluffs and anchored in concrete, were built to minimize these effects. Engineers pulled up multipath logs, searching for telltale spikes. The patterns were clean, no sign of reflected signals strong enough to fake a 6-foot leap. Next came the specter of phase unwrapping errors. In radar interferometry, a single miscalculation can turn a gentle slope into a vertical cliff. The software that processes satellite radar data has to decide how many times a radar wave has wrapped around as it bounces off the ground. Get it wrong, and you see a step where there's only a bump. The team ran phase coherence checks across hundreds of INSAR frames, comparing each jump to its neighbors. If the uplift was just an algorithm's mistake, the error would show up in isolated pixels or along the edges of low coherence zones. Instead, the vertical jump stretched in a perfect, unbroken line for hundreds of miles, across city blocks, farmland, and rocky headlands alike. Redundancy is the gold standard in geodesy. A real signal must appear in every independent dataset. Ground-based GPS, satellite radar, and old-fashioned leveling surveys. At each site, engineers compared the timestamps and raw readings. If a single station glitched, the others should stay flat. But the leap was everywhere, all at once. Tide gauges, which measure sea level relative to land, reported the same sudden drop in water height, mirroring the rise seen on shore. The odds of every instrument, every method, every network failing in the same way at the same moment, are beyond calculation. With each cross-check, the list of possible errors grew shorter. The usual artifacts, multipath, unwrapping faults, reference frame shifts, could not account for the scale or the consistency of the signal. The data didn't just refuse to break, it reinforced itself. What remained was a signal that matched no known error and no known natural process. The possibility that the land had truly lifted, without warning, without cause, hung in the air, impossible to dismiss and impossible to explain. Long before satellites tracked every tremor, the coast of California carried a reputation for instability. In 1956, a stretch of bluff in Portuguese Bend, just south of Los Angeles, began to move. Residents woke to find cracks zigzagging across lawns and roads. Over the next 7 months, the ground shifted more than 22 feet. By spring, 140 homes were damaged or destroyed, leaving entire neighborhoods in ruins. Eyewitnesses described the sensation as living on a slow-motion conveyor belt, one that never stopped, only paused and lurched forward with each new rainstorm. That ancient landslide never fully settled. Decades passed, but the ground kept creeping, sometimes just an inch a week, sometimes faster. Then, in the winters of 2022 and 2023, California was pummeled by storms that dumped more than twice the usual rainfall. The water soaked deep into the clays beneath the hills, recharging old slide plains and pushing groundwater tables to levels unseen in living memory. Sensors recorded the land moving at rates up to 30 centimeters a week, 10 times faster than anything in the historic record. The landslide zone ballooned from 380 acres to over 700, swallowing roads, homes, and even new neighborhoods as it expanded. Geotechnical teams drilled boreholes and found a new, deeper sliding layer, one that had lain hidden for decades, now activated by the weight of all that water. Municipal briefings confirmed the entire block of land was moving, not just at the surface, but deep underground. Each week brought fresh reports of buckled pavement and fractured water mains. In community meetings, longtime residents recalled the destruction of the 1950s and wondered if the land would ever stop moving, or if this was just the beginning of something even bigger. Deep beneath the rolling hills of Portuguese Bend, the hidden machinery of the earth operates with a kind of brutal elegance. When relentless winter rains seep through the soil, they don't just saturate the surface. They filter down into ancient clay layers, softening the ground and setting the entire hillside in motion. Gravity takes over, pulling thousands of tons of earth seaward along a slick, gently sloping plane. But the story doesn't end with the slide's slow crawl toward the ocean. At the landslide's leading edge, the toe, a different kind of force is at work. As the massive block of land grinds forward, its front slams into harder, unyielding rock near the coast. The result is compression so intense that the ground itself begins to buckle upward. Engineers describe this as toe uplift, a physical bulging of the land, where the advancing Earth can't move forward, so it moves up. In some global landslides, sensors have captured this rise at rates of several millimeters to a few centimeters per year. At Portuguese Bend, while the exact numbers remain unmeasured, the mechanics are unmistakable. Compression at the toe creates domes, cracks, and sudden bulges that ripple across the coastal bluff. Field teams from JPL and local agencies have mapped these features using GNSS and INSAR, tracking not just the sideways slide, but the vertical pulse at the slide's front. The data show patterns of uplift that match textbook landslide physics, even if the precise rates at the toe remain elusive. This kind of movement doesn't require an earthquake or a volcanic eruption, just water, gravity, and the stubborn geometry of the coast. The land itself, under pressure, rises in defiance of its own weight. It's a reminder that even in the absence of seismic drama, the forces shaping California's shoreline are anything but quiet. Port officials at Los Angeles and Long Beach woke to a crisis that no emergency plan had ever imagined. Container ships worth hundreds of millions lay stranded on exposed mudflats. Cranes and dock workers staring helplessly at cargo that couldn't move. In a single night, the nation's busiest ports had been cut off from the Pacific. More than $1.4 billion in daily trade ground to a halt. By noon, insurance companies were scrambling to calculate losses, and supply chain managers realized fresh produce and critical electronics would spoil or sit idle, with no way to reach American shelves. Harbor masters logged the chaos in real time. Radios crackled with reports of fishing boats perched above the waterline, their hulls resting awkwardly where tides once floated them. In Monterey, Port Hueneme, and Oakland, the story was the same. Docks left high and dry, shipping schedules shredded. Panic set in as news spread. Every major port along the coast had been crippled. On the beaches, the environmental toll became clear even faster. Tide pools that had sheltered starfish, anemones, and crabs for generations, now baked in the sun, unreachable by the receding ocean. Marine biologists from the Monterey Bay Aquarium rushed to organize rescue teams, calling in volunteers with buckets, wet towels, and makeshift pools. Hundreds of seabirds and seals floundered where the surf used to break. Emergency crews worked through the night, but the scale overwhelmed them. For every animal saved, dozens more perished. The shock wasn't limited to scientists. Locals posted videos of mass strandings, desperate rescue attempts, and the haunting silence left behind as the coastline's living edge was pushed out of reach. The human and ecological cost was immediate, incalculable, and growing by the hour. Geostride, a Silicon Valley satellite analytics firm, released their own data within hours of the coastal uplift. Their algorithms showed the same 6-foot vertical leap, but with even sharper precision than government networks. Almost immediately, the United States Geological Survey challenged those findings in a rare public statement, warning that satellite-only measurements could be distorted by atmospheric interference or software bias. Geostride fired back, accusing the USGS of clinging to outdated ground sensors and ignoring evidence visible from orbit. News outlets published leaked emails showing scientists on both sides scrambling to defend their reputations. On social media, rival experts traded barbs over calibration protocols and the reliability of open-source code. Behind the scenes, a flood of Freedom of Information Act requests targeted both agencies. Reporters demanded raw data, internal memos, and any hint of a classified military experiment gone wrong. The Department of Defense issued a terse denial, but rumors of secret drilling or underground detonations refused to die. Insurance companies, already overwhelmed by port closures and stranded vessels, saw claims spike by billions in a single day. Policies that once covered earthquakes or tsunamis were suddenly worthless, voided by a disaster with no name and no precedent. The debate over what caused the uplift quickly spiraled into a contest over who controls the narrative of reality itself. If the data was right, then the rules of geology had been broken. If it was wrong, then the world's most advanced monitoring networks had failed in their only job. With every new press release and technical rebuttal, the gap between the two camps only widened. No one could say what would happen next, or if the coast would keep rising. The only certainty was that the foundations of science, and the ground beneath millions of lives, had never felt less secure. In the past 24 hours, GPS and INSAR data confirmed vertical land movement up to 6 feet along over 400 miles of the California coast, an event no historical record or peer-reviewed study has ever documented at this scale or speed. Investigators ruled out sensor malfunction through cross-validated field audits and original file reviews. Yet the uplift pattern did not match any known earthquake, volcanic, or landslide precedent. While the Portuguese Bend case proved rapid uplift can happen locally from landslide mechanics, nothing in published science accounts for the scope or uniformity now witnessed from San Francisco to Los Angeles. Official reports from the USGS and private firms remain contradictory, with several key datasets still under internal review or classified. As ports sit idle and marine rescue teams work around the clock, California faces an unprecedented crisis with no clear scientific explanation. For now, the cause of this coastal rise is unproven, and the question of what comes next remains a matter of urgent, unsettled inquiry. Mount Etna eruption shocks. Geologists. What came out has never been seen before. Bright, glowing rock poured from the crater, defying centuries of geological records. Not basalt, not andesite. Its composition is so strange that 3 top European labs have failed to identify it. At the same time, Etna's slopes unleashed a pyroclastic flow, and seismic readings hint its deep structure is shifting, echoing conditions before the catastrophic collapse that triggered a prehistoric tsunami. If this isn't a warning, what is Etna trying to tell us? And what happens next? Mount Etna's restlessness is legendary, even among volcanoes. For more than 3,500 years, this mountain has rarely slept. Historic records and ancient chronicles agree. Eruptions are not the exception, they are the rule. On average, Etna erupts in some form more than 8 out of every 10 years. That's a higher frequency than almost any other major volcano on the planet. In the past century alone, over 60 eruptive episodes have been logged, some lasting mere hours, others stretching for months. The 2001 and 2002 events, for example, sent lava and ash across the Sicilian countryside, forcing evacuations and grounding flights. But even those dramatic moments are just the latest in a long chain. Archaeologists have traced layers of ash and lava back through Roman times, and even further, to Bronze Age settlements buried beneath black rock. Each layer is a timestamp, marking yet another burst of energy from deep inside the earth. Paroxysms, those violent, short-lived eruptions, have become almost routine here, with more than 50 recorded since the early 20th century. Etna's activity isn't just a spectacle, it's a relentless process that shapes the land, feeds the soil, and disrupts the lives of everyone living in its shadow. The volcano's constant output means that new craters, cones, and lava fields appear with startling regularity. In some years, the summit changes shape multiple times. Vents open, close, and shift position, as if the mountain itself is breathing. This long, unbroken record of eruptions sets Etna apart. It's not just a volcano that erupts. It's a volcano that almost never stops. That unyielding activity is the surface signature of something far more complex happening beneath the ground, a hidden blueprint of chambers, conduits, and shifting faults that scientists are only beginning to map. Deep beneath Mount Etna, the story of every eruption begins in a hidden world of molten rock and shifting pressure. Scientists like Boris Behnke have spent decades piecing together a map of Etna's interior, using seismic waves and chemical signatures as their guide. At the base of this system lies a vast reservoir, nearly 11 kilometers below the surface, a depth where temperatures and pressures are high enough to keep rock in a perpetual state of melt. This isn't a simple single chamber. Instead, Etna's plumbing stretches upward in tiers, with magma pausing at several levels before making its final push to the summit. Each reservoir acts like a staging area, where new magma mixes with older batches and picks up clues about its journey. The lava that typically reaches the surface carries a familiar fingerprint. Petrologists describe a mineral trio, olivine, clinopyroxene, and plagioclase, as the backbone of Etna's rocks. These minerals crystallize out as magma cools and rises, locking in information about temperature, pressure, and even the source of the melt. Most eruptions produce basaltic lava, rich in iron and magnesium, with a composition that matches what's expected from a mantle-derived source, modified by its passage through the crust. Over the last 50 years, careful analysis has shown a steady trend, a gradual enrichment in potassium and strontium, likely from the assimilation of sedimentary rocks as magma rises through the upper 10 to 15 kilometers of crust. But even with these shifts, the basic signature remains consistent. Etna's lavas are well documented, their mineralogy charted in detail across thousands of samples and decades of research. This baseline matters. It gives scientists a benchmark for comparison, a way to spot anything out of the ordinary.